Imagine trying to play a piano with oven mitts on. You aim for one specific key, but you end up striking 5. This blurred resolution is the daily reality for current cochlear implant users, because electricity naturally spreads through the ear like a puddle, stimulating overlapping nerves. Our goal is to take off the mitts. By moving from broad electrical broadcasting to the surgical precision of light, we can target individual nerve clusters without the interference. Today, we're going to show you our COMSOL multiphysics model that suggests this waveguide-based optical stimulation is the answer to bringing high-definition sound to the inner ear. To understand our solution, we first have to look at the elegant mechanics of the human ear. Normal hearing is a multi-stage energy conversion. Sound waves are captured by the outer ear, amplified by the middle ear bones, and sent into the cochlea. In the inner ear, fluid displacement physically bends tiny hair cells, converting mechanical vibrations into the precise electrical impulses that the brain interprets as sound. We turn to cochlear implants when this mechanical to electrical bridge is broken, specifically when the hair cells are damaged or missing, but the underlying auditory nerve is still functional. In these cases, we have to bypass the machinery of the ear and talk to the nerve directly. Traditional cochlear implants rely on electrodes to jumpstart the nerve with electrical pulses. However, the inner ear is filled with perilymph, which is a salty, highly conductive fluid. Because of this conductivity, electricity spreads out like a puddle rather than a focused point. So this lack of spatial selectivity, which is the physical focus of energy, degrades the spectral selectivity, or the user's ability to distinguish between different sound frequencies. Our solution shifts the medium from electricity to light. By using optogenetics, which is genetically modifying nerves to be light sensitive, and optical waveguides, we can point a beam of light with laser-like precision. Unlike electricity, light does not leak or spread across the conductive perilymph. It maintains a tight, focused trajectory. This transition from broad electrical broadcasting to precise optical targeting allows us to stimulate distinct neural populations, providing the high-fidelity frequency resolution required for a truly detailed spectrum of sound. The inner ear is a perilymph-filled cavity directly embedded within the skull, and it acts as the primary interface between physical sound waves and the brain, and I've highlighted some of its key structures here. The cochlea is a 2.75 turn logarithmic spiral structure within the inner ear, and it's designed to mechanically separate sound by frequency. And I've noted here how the electrode fits into the scala tympani region of the cochlea. For our CAD model, we built the cochlear geometry entirely from scratch. To do this, we started by taking cross-sectional images of the cochlea and recreating those profiles as sketches. Then, we used a loft operation to connect these cross-sections along the length of the cochlea, which allowed us to generate the smooth spiral geometry from the base to the apex. This approach let us control the shape while still keeping it anatomically representative. We also positioned the waveguide and auditory nerve regions within this geometry so that we could properly study how light waves travel through the system. Overall, the goal was to create a simplified but realistic model that captures the key spatial relationships needed for the optical simulation. To model this accurately, we used a 3D model because light rays reflect and refract in 3D, and this allows us to capture its true behavior as it navigates the human cochlea. We've modeled the scala tympani and the auditory nerve using a refractive index of 1.35. While neural tissue can slightly vary, water serves as a scientifically sound baseline for optical propagation in a fluid-filled environment. One key assumption we made is treating the perilymph as a stable medium. While it is technically a fluid, its motion does not significantly impact the trajectory of the light rays in our study. The core of our design is the silicon waveguide. It acts as a high-precision delivery pipe using its high refractive index contrast to confine light within its core. This allows us to steer the beam past the fluid and bone and target specific neural populations. Finally, we've encapsulated the entire system in the bony cochlear wall, simulating the densest bone in the human body to ensure our model reflects the true anatomical constraints.
We use light to improve the spatial precision of auditory nerve stimulation compared to current cochlear implant technology. Optogenetics relies on light to activate the auditory nerve with much higher spatial resolution, and this is achieved through genetic modification of tissue, where neurons are engineered to express light-sensitive ion channels. And when illuminated, these channels trigger neuron activation in very specific regions, which allows for more targeted stimulation. This increased precision demonstrates the potential for improved frequency selectivity in cochlear implants, which could ultimately lead to a more natural and clearer hearing. So looking at the physics, the ray position equation tells us that light moves with a group velocity, and it describes how rays propagate through the space by the wave vector, which is k. The ray direction equation tells us that light changes when crossing materials of different refractive indexes. So it'll want to go to the material with a high refractive index, which is really useful for our simulation. And then the directional release boundary condition just tells us that we spray the rays out like a cone at the base instead of in a straight line. As for the boundary conditions, to model light propagation, we defined these to control how the rays enter, interact with the nerve, and then exit the system. So light is launched from the base of the waveguide with a defined release direction to ensure consistent propagation. And then also there's a stick condition applied at the nerve interface. So that's where k is equal to 0, so there's no more propagation of the wave, and this is to more accurately capture and look at the absorption of the rays after contact. In our model, we make several simplifying assumptions to focus on the key physics. So first, we assume that light is fully absorbed at bone boundaries, so that means any rays reaching bone are terminated without reflection or transmission. Secondly, we model only a single waveguide to isolate the behavior of a guided light delivery. And finally, we use a discrete ray approximation, where light is represented by a finite number of waves instead of a continuous electromagnetic field, which simplifies computation while capturing overall propagation trends.
Here, we show the ray trajectories for the conical release case. In this setup, rays are emitted from the waveguide within a cone, with directions spread uniformly. As a result, the rays diverge quickly as they move through the medium. From the plot, you can see that this spreading reduces how concentrated the light remains, which makes it less likely for rays to reach the auditory nerve region. So overall, this release method leads to weaker targeting and lower effectiveness. In contrast, this slide shows the expression-based release. Here, the ray directions are more controlled, which keeps them more focused as they propagate. You can see that the rays stay more aligned and directed towards the nerve region. Because of this reduced divergence, a larger portion of the rays are able to reach the target. This demonstrates how controlling the emission profile can significantly improve spatial precision. Finally, we calculated the efficiency as the percentage of rays that reach the auditory nerve. From our results, we obtained an efficiency of about 90%. This means that the majority of emitted rays are successfully guided to the target region. This high value is consistent with what we see in trajectory plots, where more focused rays lead to better targeting and less loss to the surrounding regions. In particular, fewer rays are lost to the bone boundaries, where they are absorbed and removed from the system. However, it's important to note that this is likely an overestimate, since our model does not include effects like scattering, partial absorption, or reflections within biological tissue. In reality, these effects would cause additional losses and reduce the overall efficiency. Even so, the trend shown in both the graphs and the efficiency calculation is clear. Improving the directionality of light significantly increases how effectively it reaches the auditory nerve, which supports the use of optical methods for more precise and localized stimulation.
So some weaknesses and future considerations of our model is that our model is pretty simple, so we only include key anatomical structures like the bone, the scala tympani, and the auditory nerve, and also only one waveguide was modeled. And these limitations matter because they may underestimate the light scattering and loss in real tissue. So how we would improve this in future iterations would be to add more realistic cochlear anatomy, and to also include properties of different tissues that exist in the ear to see how loss would occur
Our first priority would be to optimize the hardware design by modeling how different micro LED sources and waveguide geometries would affect light confinement. We want to test various configurations to see which ones deliver the tightest, most efficient beam and ensure our device has the smallest possible physical footprint while maintaining maximum power efficiency. Next, we would like to develop a parallel COMSOL model of traditional electrical implants to directly quantify the improvement in spatial selectivity. Furthermore, we would want to refine the bony cochlear wall boundary to account for backscatter and diffuse reflection. Since this bone is highly dense, modeling its reflective properties is essential to ensure that stray light doesn't cause optical crosstalk. Thank you very much for your time.